Today we're going to talk about what happens when we aren't finding the full circumference in the circle or the full area of a circle if we only want part of the circle for either circumference or area. Now, really it's pretty much the same thing either way. The only real difference is if we're looking for arc length or part of a circle for part of the circumference, we're going to use the circumference formula as a basis. And if we're looking for part of the area, we're going to use the area formula as a basis. So I group them together because essentially they're doing the same thing with the two different concepts of circumference and area. You'll also note it comes down to a proportion, which really makes sense because we're talking about a proportion of the circle. So if I'm only looking for the length of the arc from A to B, and by arc length here I'm not talking about the angle that we talked about before. We talked about arc angle, or the measure of the arc, and the measure of the arc was the same as the measure of central angle. That's fine. Now what we're really saying is, what if I take this segment AB, this arc AB, and I were to measure it for its actual length? How many inches, feet, centimeters long is it? So that's what we're doing now. And it's a proportion. It says the arc length of AB over 2 pi r, which is the circumference, is the measure of arc AB, or the measure of the corresponding central angle, which is the same, over 360. If we solve the equation for the measure of arc length AB, we basically multiply both sides by the denominator, and I get the measure of the angle over 360 equals 2 pi r, times 2 pi r is the measure of the arc. So this is just a rearrangement of the formula. The way I usually like to do it is arc length, which I'm going to abbreviate L with a cursive L here, over circumference, which is pi times diameter. Let's use that formula since we were using that before, equals measure of the central angle, theta. I'm going to use that for the measure of a central angle over 360. And again, all they're doing up above is redoing that, redoing this equation by multiplying both sides by pi times diameter to get arc length by itself. Now, this is pretty straightforward and it really makes sense. Because, for example here, if this angle represents 1/4 of the circle, 90-degree angle, then we'd expect this arc length to be 1/4 of the circumference. If it was 1/8 of the circle, we'd expect the arc length to be 1/8 of the circumference. So it's proportional, and that proportion makes sense. Let's try it a little bit. Find the arc lengths indicated here, or the information using that formula indicated here. The reason why I like the original formula is because our unknown could be anywhere. Maybe I know the arc length, I need to find the diameter. Or maybe I know the arc length and diameter, I need to find the measure of the central angle. It really doesn't matter which one is unknown. This formula, this proportion, lets me fill in the blanks that I know and leave the unknown out and solve for it. So my unknown sometimes is going to be the arc length, sometimes it might be the diameter or the radius of the circle, sometimes it might be the angle. It's fine. We can use our formula any way we want. So here we're looking for the arc length. So arc length is unknown over the circumference of the circle. Now here the radius is 8, so the circumference would be 16 pi. Because diameter is 16 if the radius is 8, and circumference is pi times diameter, equals the measure of the angle, which is 60, over the entire circle, 360. To make life easier, I'm going to reduce this fraction. 60 over 360 is 1/6, equals arc length over 16 pi. When I cross multiply, I get 6 times the arc length equals 16 pi, and divide both sides by 6. Arc length equals 16 pi over 6, which I'd reduce to 8 pi over 3, and set my context centimeters. So the arc length is 8 pi over 3 centimeters. We could, of course, decimally approximate that, but with a nice whole number like that, being consistent with what we did yesterday, we aren't going to. Second example here, the arc length is known. We're looking for the circumference. Fine, not a problem. Arc length, same formula, arc length over circumference, which I don't know, equals, and when we got our 40 over 360. And I could reduce that to 4 over 36 or 1 over 9 if I wanted to, or I could leave it as 4 over 30. I mean, I'm going to cross multiply. It's going to work its way out either way. And since it's decimally approximate, we're just going to go ahead and multiply those numbers. So 360, well, I'll do it at 36 to make it easier, times 4.19, okay, equals 4c. So I divide both sides by 4. So 36 times 4.19 times 4.19 divided by 4 is 37.71. Circumference of the circle is 37.71 inches. All right? And again, that kind of makes sense. 40 degrees is 1/9 of the circle, because 40 out of 360, 40 is 1/9 of 360. 360 divided by 9 is 40. So I'd multiply that by 9 to get to this, and that's exactly what we're doing. Same formula. It was a different unknown, but it was the same formula. We just put our unknown in a different spot. Here I know the radius of the circle, and I'm looking for the measure of arc RS. Now, since it said RS, we know we're going to go the short way. Okay? But notice it's not arc length RS. It's the measure of the angle that's unknown, the measure of arc RS. We're looking for that theta, which is going to be the same as this theta right here. Okay? We know the arc length is 44. We know the radius circle is 15.28. Decimal problem, we're going to have decimal solution, but it's the same formula. Arc length over the circumference of the circle. Now, we are going to have to find the circumference. So off this side, the diameter is 30.56, twice times 15.28. So 30.56 times 3.14 gives me 95.95. So we'll call it 96. Well, 95.96. 95.96. We'll be consistent with our two decimal places. Equals, the unknown this time is my theta, over 360. And we just cross multiply. 44 times 360 is 15,840 equals 95.96 theta. And I divide by 95.96 divided by 95.96. Try again, divided by 95.96. Hit the right buttons. I get 165.07. Okay, and the context is degrees. So here we see we use the same formula all three times, but the first time my unknown was the arc length. The second time my unknown was the circumference, which if it was the radius or diameter, we could probably figure that out from once I know the circumference. The third time my unknown was the angle. It doesn't matter. It's the same formula. We fill in the blanks we know. We solve for what we don't know. Again, finding the arc length of PQ. So more of the same. Arc length is unknown this time, so there's my unknown. Over, I know the diameter is 9, so 9 pi equals 75 over 360. Now, I'd probably want to reduce 75 over 360, which I can do very quickly in my calculator, is 5/24. 9 pi, sorry, not 95. So it's 5 over 24. So 5 times 9, that's 45 pi over 24 equals my arc length when I do the cross multiplying and dividing. And we should add units to that, so it's yards. Same thing here. It wants the circumference is my unknown. I know the arc length is 61.26 over the circumference equals the angle over 360. Now 270 over 360 is 3/4. And so 3C equals 4 times 61.26, which is 245.04, divided by 3, and 81.68. And again, we should give units, that's meters, context. All right, let's start this one. We're looking for the radius of the circle. Now, this is just like this previous problem in that we're going to have to start by solving for the circumference. It's just that once we know the circumference, then we're going to have to work circumference formula backwards to find radius. So getting you started here, I know the arc length. I don't know the circumference equals central angle over 360. And 15 over 36 is a reduction, and 15 over 36 reduced is 5/12. So I'm going to let you finish it from there. Remember, I'm not solving just for the circumference. I need to find the radius. So please do that. Second part of this is really exactly the same, except we're doing area instead of circumference. So now instead of just finding the arc length, we're finding the area of this. But the context is exactly the same. The sector area, which we usually abbreviate S, over the area of the circle equals theta over 360. So the only thing we're really changing is we're using an area formula instead of a circumference formula because we're looking for an area instead of a length. So if we want to find the area of the sector in this picture, the red sector, sorry about the announcement going on. But what we're going to do is we're going to take the area of the sector over the area of the circle, which is pi r squared, equals 70 over 360. So, once again, I know the radius is 8, so that's 64 pi. And I'm going to make that 7 over 36. So I cross multiply. 7 times 64 is 448 pi equals 36 times the arc length, divide by 36. And 448 divided by 36, and we switch that to a fraction, is 112 pi over 9 equals the sector area. Now, would it be reasonable to decimalize that? Maybe, because 112 pi over 9 really doesn't show me very much. And if we wanted to, we could decimalize right at this point. But it is nice to have an exact answer, too. Here we go again, another one of finding the sector area. So once again, it says find the area of the red sector. The red sector is 120 over 360, or 1/3 of the circle, right? When that has to equal the sector area over the total area, which would be 14 squared, which is 196 pi. So S over 196 pi equals 1/3. When I cross multiply, I get 3S equals 196 pi. Dividing by 3, my sector area is 196 pi over 3. Now you get to try it for the area of the blue sector. the question you have to ask yourself is, what's the measure of that central angle? And we'll go ahead and leave it in terms of pi. Finally, this formula can be worked backwards also. If I know the area of the sector, I can go ahead and work backwards to find the area of the entire circle. So area of the sector is 35. Notice it's not in terms of pi, so we will decimalize. Over the area of the circle equals 40 over 360. Cross multiply that. 35 times 360 is 12,600 equals 40 times the area. Divide by 40. 1260 divided by 4 equals 315 meters squared equals the area. So again, same type of formula, plenty to do here. We're going to spend a couple days on this in applications. We'll see you in class.